Hi, I'm Walter, and welcome to Flight Path Pioneers. This is a helicopter lesson in 15 minutes or less. We'll continue on our advanced aerodynamics. I'm going to take apart three different phenomenons, one at a time, because it's important to kind of let that sink in. And these are difficult lessons to grasp as a new student. And you will learn these things and start understanding them as you proceed through your training. But again, it's a good introduction. And we're going to start off with Dissymmetry of Lift. The phenomenon is we talked about the components of the aircraft itself, about the main rotor blade system, and we started understanding on each of the components and what they do. So if you go up to the rotor mast again, go outside, climb up the aircraft, touching, feeling, seeing is the way to learn best. We have talked about the flapping, we've talked about the hinges, we've talked about the pitch horns, how the swash plate, the upper part, the lower part, how it all works in connection to the tubes that connect you to the cyclic and the collective, and of course the tail rotor to your pedals itself. Now, because we don't have a wing that extends like an airplane outside of our left and right side, we have a rotor that acts like a wing, but that is in circles. And if you look at the blade itself, there is a leading edge of the blade and there's a trailing edge of the blade. Of course, when it goes forward, the trailing edge, the leading edge is hitting the wind first, the relative wind first, and then of course on the flip side, on the opposite side, the trailing edge is exposed, right? And the wind is going in the opposite direction from that. So just by that phenomenon, you think that one side is going to generate more lift than the other side, right? Because you can't have it both ways. So that is something to really, is rather difficult to in a concept to understand. We're going to dive into it a little bit, in a minute. So the question often comes up: do aircraft, helicopters have a speed limit? You will see that the speeds vary by the type of aircraft you fly, and the answer is yes, there is. Because at some point in time, the rotor system, as it has a constant RPM, cannot keep up with the adjustments that are being made to cancel out the dissymmetry of lift on the left and right side, which can cause a stall. And a stall reduces the amount of lift being generated by that rotor, as we learned in a previous session when we talked about rotor blades and components. That can cause vibration and a roll. And again, those things you have to take into consideration, and we have to learn a little bit more about. Now, trust me, you will not be flying your aircraft anywhere near VNE as a student. But as you become a commercial pilot and you're flying for time and distance, you might be pushing it by having a max continuous power setting, and depending on the wind conditions, the outside environment conditions, you might be going fast enough to get into that zone where you can get into some sort of stall of the blade itself. So again, these things are relevant and we need to learn about them. It is not something you can simulate or should be simulating. It's something you need to be aware about. So let's take a look at what that actually means. We learned about the equation earlier in a couple sessions, and although you won't be doing these calculations in the flight itself, but the principle of the symmetry of lift is something that you need to understand. So the definition of it is the unequal lift of two halves of the rotor disc due to unequal relative airflow. So I want you to concentrate on that picture on the right hand side. Again, the helicopter is facing upward, right? Let's say call this the north. And the wind, the relative wind, is coming straight at the nose. So forget about any crosswind. It's coming straight at the nose itself. Well, as our rotor system is turning counterclockwise, the right blade on the right side is exposing the leading edge of the blade itself, versus if you look at the other side, at the 9 o'clock position, that will be exposing the trailing edge. So even though the tip speed of both are going to be equal at 400 knots, right, the amount of lift that is being generated is different, right? It's 400 plus 100 on the right side equals 500, while it is 400 minus 100 on the left side. And that becomes critically important, right? Just by the numbers alone, you understand that the advancing blade is going to generate more lift than the other side. And if that happens, obviously we cannot maintain a stable flight and we'll be in a constant turn or dipping. So the aircraft has to overcome that. Now, the manufacturers of the aircraft, of course, took that into account and started thinking about how can we possibly compensate for that. So there's nothing that you need to do. The only thing, your role, as we talked about, is not to go too fast, right? Not to exceed the VNE for the day's condition. We'll talk a little bit more about that. So the way the rotor system was set up in the Robinson helicopter, and it slightly varies from helicopter to helicopter, but our semi-rigid rotor system, right, that gives that flexibility, is compensating for the dissymmetry, the difference between the lift component on the left side versus the right side, by blade flapping. Now, we talked about in basic aerodynamics that if you have a rotor blade that is symmetrical and then is going to be in a neutral position while you're on the ground, and as you increase the angle of attack, you're going to create lift, and at some point the lift will be greater than the weight, and therefore you can take off. Now, as soon as you take an angle of into the blade, something needs to happen to offset the dissymmetry. So the way that it does it is on the left side of the aircraft. It will be where the more lift is generated on the advanced side. The blades will flap up, decreasing the angle of attack. Remember, the angle of attack determines how much lift we're going to get. So we want to have less lift on the right side. We have to flap up, causing a decrease in the angle of attack. Because the opposite is going to be happening on the right side, right? So you have one flaps up, the other one flaps down, increasing the angle of attack, therefore increasing the lift component. And through that, it equalizes. So therefore, you have an equal distribution, and you can, have horizontal flight through the action of flapping. And this happens so fast you cannot see it with your bare, with just looking at it. There are some really good video clips on YouTube, and I would encourage you to go to that and take a look at it to visually see how that, what takes place in real time. Now, mind you, the main rotor is spinning 500-600 times per minute, right? With the naked eye, it's impossible to see. But that mechanism works perfectly up to a certain point, right? If we increase the angle of attack to the point of critical, the critical angle of attack in excess, remember the left side, we are flapping up and decreasing the angle of attack, which is fine. On the opposite side, on the left-hand side, right, the retreating blade can be impacted if we have too much angle of attack put into it. In other words, we get to that critical angle of attack, and that's where a disturbance of air can create what we call a stall. And that is something that we need to, again, take into consideration and on the ground. And why and how do we do that? Well, first of all, we have to have a good weight and balance. And the second thing we need to take into consideration the outside conditions of temperature, humidity, density, altitude, to understand on how fast we can go, right, the never exceed speed limit for that particular day. Now, there's a chart that you can find in your aircraft that you can calculate your VNE for that particular flight. So, for example, for the R-44, under normal conditions, the not to exceed is 130. I think that VNA for a 22 is 102. That's on a given day. But that always needs to be adjusted for the date of flight, taking into account the external factors. All right, so knowing that, measuring that, and I will show you in a chart in a second where you can find that and how you can calculate that out. Knowing that, you also understand that if you're going flying and you're going fast under these conditions, there comes a point in time that the left side, the retreating blade, can exceed the critical angle of attack and is causing two things. We're causing a stall at the tip, the far end, the tip of the blade, decreasing the amount of lift that can be generated by that, but also in slowing down and at the root of the blade itself. So that two of these areas are going to be impacted. And again, we need to have lift surface, right? That's part of the lift component, the calculation, the equation, in order to be able to generate. Now, we're already struggling on the left side because of the retreating blade, and this will be accentuated if we don't correct it. Now, the good thing is that as soon as that happens, there will be early indicators like vibrations, and we're pitching up. Remember, the input at 9 o'clock is felt 90 degrees later, right? That's per session. And therefore we will be pitching up, right? We're losing and then we're pitching up. The best thing, recovery, is to lower the collective, to take the angle out, right? To reduce the critical angle of attack back to within normal limits. And a gentle application of aft cyclic to slow down. So how do we stay out of this? Don't go too fast. How do we recover from it? Lowering collective and gentle aft pressure on the cyclic to slow down. If you have turbulence outside, again, that is another reason why your pilot operating handbook will tell you to not exceed 70 or 90 knots, depending on what aircraft you're in. Right? All these things matter that you during flight, and you need to learn them, of course, on the ground and in theory, because you never want to get yourself into that particular position. So in your chart, and this should be on your checklist, that every single time you go out, you take that out and you look at the never exceed limitations, and you look at the altitude that you're flying at, you look at the outside air temperature, and then you make an assessment to what is the VNE for that particular day. You write that down, you keep it in the back of your mind. It's not the red line on the gauges, right? That changes depending on the outside conditions, something that you need to think about. All right, next lesson is about loss of tail rotor effectiveness. I'll see you at the next lesson. Thank you.